Hello guys, welcome on Tesla Adventures. Now in this video, we'll discuss the importance and significance of elastic potential energy in elasticity. So we have already discussed the elasticity in the previous video, and it was the fact that when some body is deformed from its original shape or size, then it tries to regain its original shape and size. And to regain the original shape and size, a deforming force is developed in that body. So this phenomena or this property of that body is called as elasticity. We have already discussed in detail. Now we have discussed that when the body is elastic, then the deforming force developed in it is conservative, and therefore the work done against that conservative force is converted into the potential energy, which is called as the elastic potential energy, and that energy is completely recoverable. We can recover that energy from any point of time. But when body is dragged into the plastic region, then the non-conservative forces are acting in the body, and the energy involved in that body is not recoverable. So we are here to discuss about elastic potential energy. So by definition, we can say that the elastic potential energy is the work done against the internal restoring conservative force when a body is deformed. Okay, so this is the elastic potential energy. So when that restoring force is trying to regain the body its original shape and size, and we have removed the deforming force, then we can say that elastic potential energy is recovered back in form of vibrational energy, heat energy, light energy, or sound energy. Okay, so if we observe the graph of potential energy of a pair of atoms inside a solid crystal and the interatomic distance r, or we can say that it is a graph for a matter. Okay, so this is the distance between the two atoms, and this is the potential energy of that two atom system. So we already know that when that body is not deformed, it is in a stable equilibrium and its potential energy is minimum. So this point represents the minimum potential energy of the body, or we can say the potential energy when the body is in relaxed state or non-deformed state. But when we deform that body, then we already know that it would that distance, let's suppose we have compressed that body, so the minimum distance between the two points between the two atoms decreases, and the maximum distance also increases. So we can say that on deformation, the potential energy increases. You can see that this potential energy is going up, and let's suppose we have deformed the body till this point, so the final potential energy till this point is U. So this is the potential energy of the deformation of the body. Now what is the elastic potential energy? So the elastic potential energy is the work done in deforming the body. And we know that when the potential energy of a system is increasing, then the work done is the change in potential energy. So we can say that the work done by us, where us is referred to as external force, and therefore the work done by external force or work done against the internal conservative force is this U minus U minimum. Okay, so this is called as the elastic potential energy, and this energy is stored inside the body itself. So now what is the expression for elastic potential energy? So let us derive the expression. So let us consider that there is a wire whose relaxed length is L. Okay, and we have slowly stretched this wire by a distance of x. So the deforming force, now when we say that we have slowly stretched the wire, it automatically means that the rate of deformation is so small so that the acceleration is zero, and for zero acceleration the net force acting on the body is zero. Now net force zero means that the external force applied by us and the deforming force developed in the body are equal and opposite in directions. So we are assuming that this deforming force, or this restoring force in fact, and the external force which we have applied are equal and opposite in directions, and therefore we can write that Fr is equal to F external. Now if we have to find out the value of F external, so we can say that stress will be equal to F restoring upon area, and it would be equal to gamma into strain. Now strain will be the change in length upon original length. When we have stretched this wire, then its length changes by a distance of x and its original length is L. So the restoring force is equal to gamma A by L into x. So if we compare this force with the spring force which we have already discussed in mechanics, that it was F is equal to kx, then we can also derive a fact that K, spring constant, is equal to gamma A by L. Okay, so this is also a conclusion of this derivation. Now we know that when we have stretched this wire, when we are stretching this wire furthermore by a distance of dx, you can see, then the work done by external force dw will be equal to integration F, in fact small work done, will be equal to F external into dx. So dw will be equal to F external, which is kx, because we have assumed that the restoring force and external force are equal in magnitude, and the restoring force is kx if we are comparing it with spring. So kx dx. Now the total work done in stretching this spring is integration kx dx, and total work done will be k, this is x square by 2. So limit is also 0 to x. So work done is equal to kx square by 2. Or we can say that the energy is stored, elastic potential energy. Elastic potential energy is equal to half kx square, which we have already derived in mechanics. Now this k is equal to gamma A by L, and u is equal to half gamma A by L into x square. You can see that if I write it down as half gamma A into x by L, and if I multiply and divide both sides with L, so you can see that x by L is strain and u will be equal to half gamma A into L into strain square. So this is the volume of the wire, and the energy density, U is energy density. So energy density will be equal to energy per unit volume. So it is U is equal to half gamma into strain square. So this is one formula for the energy density of a wire which is stretched or deformed. And now if we move on to the another form of this formula, so first of all let us write down this form, that it is gamma into strain square. Now we know that gamma into strain is also equal to stress, so it is also half stress into strain. So this is an important formula. So this is form number 1, this is form number 2, and if we replace strain, if we replace this strain by stress upon gamma, so we can say that U will be equal to half stress square upon Young's modulus. So let me again remind you that this is not the energy, and it is energy per unit volume of wire, which is also called as energy density. And I would recommend you that whenever in numericals you are calculating the energy, you should use the formula half kx square, and k is equal to gamma eval. So you can use this analogy of spring, and I would be making another video which would depict the spring analogy to solve the elasticity problems. Thank you.